So when we left off, we just explained how the whole ANOVA table for regression works. But we kind of left vague what's going on with something called an F statistic and why we calculate that. Well, early on it was recognized that you can construct this table for any given regression. And for any given regression, you can also imagine that you could calculate a score, which would be the ratio, in this case, of the mean squares associated with the regression to the mean squares associated with the error. Now, as your mean squares associated with the regression go up and your error goes down, you're going to have a higher overall explanatory value of your regression. It's similar to what we talked about with R squared. As your error term here goes up and your mean squares regression goes down, the opposite thing happens. So we generally are going to, our regression equation is not going to be doing a very good job of explaining variation due to error. So if we graph this out across a number of different situations, we can end up with a curve Well, that's not a nice pen. We can end up with a curve that will be the distribution of F scores. So my F score might be on my x-axis and my probability of getting a given score be on my y-axis. It turns out this is a skewed distribution when you calculate this for in a number of different situations. And if there's no real relationship and you're just randomly sampling points and occasionally getting a line out of the points that you sample, that turns out to be kind of a rare occurrence, and you end up with a really high F score, which would be a rare probability in the case that there's no real relationship. So most of the time, if there's no real relationship, this is going to end up being a low F score is going to be the common situation. As you get higher and higher F scores, there's a lower and lower probability that you'd get that due to chance. In other words, there's probably something real going on here. So as your source of variation, your sums of squares related to your regression becomes larger and larger, there's a higher and higher chance that that's really that it's a real pattern. I don't feel like I'm explaining this very well. Drop something.
Well, let's take a look at this ANOVA table one more time. So we have our sources of variation. We have the regression, we have error, and we have total variation. So this here represents the variation in your overall data set that can be explained by the line. This represents the variation in your total data set that's not explained by the line, that's like noise around the line. And this, of course, is something you're familiar with, total variation in your data set. Now, the degrees of freedom for regression are kind of confusing, but if you want to think about the variation just one more time, you want this value to be high, you want this value to be low. Oh, that's kind of what's happening over here. When this value is high and this value is low, your F score goes up and you end up out in this tail. That's where you want to be if you have a linear relationship between your data points. So the degrees of freedom are kind of confusing for regression. There is always one degree of freedom for the line, for this regression term. Always. Doesn't matter how big your data set is, there's one degree of freedom to basically predict, to understand the line, the prediction of the line. Now, where all of the rest of your degrees of freedom end up are in the error term. And you have, in terms of this error term, you have all of the points in your data set. And to understand the line, you have to estimate both the slope and the intercept. And so that's why there are n-2 degrees of freedom for your error term, because you need 2 degrees of freedom to estimate the slope and the intercept. Now remember, for your whole data set, you only have to estimate the grand mean, and so that's why there are n-1 degrees of freedom. Only those are the values that are free to be whatever they want to be. Okay, So let's think a little bit more about degrees of freedom because they're kind of a confusing topic. I like to think about it this way. So consider we have a set of numbers. I'm just going to say I have a 3, I have an 87, and I have one more number. Now, if I don't know anything about this set, this last number could be anything. It could be 0, it could be negative 2,000, it could be 152, right? If I don't know anything about the set of numbers, all 3 numbers are free to be anything they want to be. But if I know something about the set, like the sum of these 3 numbers is 100, now all of a sudden, these 2 numbers are still free to be whatever they want, but this last number, it's not free anymore. So it has to be 10, right? So the degree of freedom for this set of numbers would be n minus 1. It's always, well, it's often n minus 1 if you know one thing about the set. Now in this case, for the regression line, we know 2 things about the regression line. We know both the slope and the intercept, and so that's why 2 numbers, in terms of the error term, are not free to be whatever they want to be.
So that's degrees of freedom. And now let's go back to our F-score. Now remember, there were 2 things we needed to know about our regression. We had 2 big questions. The first question was, one of our questions was, how strong is it? We got an answer to that question by comparing our sums of squares regression with our sums of squares total, and we had an R squared value. Our next question was, is it real? What did we mean by is it real? What we meant is that when you get a sample of points and you fit a line to it, sometimes, just like we started, you could fit a line entirely due to chance. In fact, in the case of having only 2 points in a data set, at the very start we covered the fact that you will always get a line just due to chance in that case. So what about an intermediate case where we have a few points and we fit a line? Would we get that sample due to chance, or does there have to be a true relationship between x and y? The easiest way to do that is to test the null, and the null would be that we're getting this just due to chance. In order to generate an expected set of values for a null distribution, we can take a data set where there's no relationship between x and y. Let's use a different color here. It may show up a different color for you. And let's take a situation where there's no relationship between x and y. We just have a random scatter. We could go through and randomly sample, and sometimes, just by chance, we could randomly sample points that would form a negative relationship here. Okay? That's possible. That would be one random sample. We could randomly sample and find absolutely no relationship. Randomly sample like this, and it would be a good representation of our data set, and we get nothing. Or we could randomly sample and find a positive relationship. So randomly, we can pick points that just so happen to show a relationship, even when there's none present. That's where the F-score comes in. The F-score calculates the ratio between the regression mean squares and the error least squares in the case where there's no real relationship. If we take a data set with no real relationship and we calculate the F-score, we find that most of the time we don't find the last case I drew here. Most of the time, when you sample a data set, bear with me while I erase the green marks here. Most of the time, when you sample a data set where there's no real relationship, you will end up sampling points that look something like this. They're just a random scatter within a random scatter, and you're going to end up with an F-score that's relatively low. That is, your mean square regression is not going to be that different from your overall mean, and your mean square error is going to be much larger. Okay, so you're going to get a small F-score. And so your F-score is going to be somewhere here. But occasionally, just occasionally, you're going to accidentally do a random sample, and you're going to end up randomly sampling points in such a way that you get a line that deviates from the mean by quite a bit. When that happens, when that line deviates from the mean quite a bit, we end up with a high MSR. We end up with a relatively low MSE, close fit of those points to the line itself. And we end up with an F value that's very high, and that has a low probability under the null. So this F distribution is constructed under null expectations. The null being that the regression line actually looks a lot like the mean of the overall points. That's really the null we're testing. We're testing the null hypothesis that our regression equals the mean, essentially. That lets us say, is it real? If we end up with a high F-score, which is a low probability, then there's a low probability of the null. So if our null has low probability, that's the same as saying, or similar to saying, yes, most likely real. You might be able to read my chicken scratch there. So, for that, for is it real, ultimately what we're looking at is a p-value. And that p-value is the F. It comes from our F-score. So we calculate a high F-score, we get a low p-value, like here. And when that p-value is less than the often used 0.05, which we'll generally use for our regressions by default, then we say there's a low probability that the null is true. And so we can rule that out, we can reject the null,